Every day, the future's getting closer.
Welcome to Master the NEC, where we talk about the National Electrical Code and all things electrically related. My name is Paul Abernathy, your host, and welcome to today's podcast. Well, hello everybody. Welcome to another episode of Master the NEC, where we talk about the National Electrical Code and all things electrically related. My name is Paul Abernathy, your host. Welcome to the podcast. As always, I appreciate you taking the time to listen to these podcasts and to share them with people. Hopefully, we're all learning together. There's no know-it-alls here. Everybody's learning something together, and that's what it's all about. So, on today's podcast, we're going to dive into grounding and bonding a little bit. We're going to talk about main bonding jumpers and system bonding jumpers just a little bit, but probably spend most of the time talking about main bonding jumpers because we kind of take those for granted, and they have such a vital role in making sure that we have safe electrical systems that sometimes we spend a lot of time looking at equipment grounded conductors, and they're extremely important. And in order to be able to allow fault current to get back and clear an overcurrent device, we get it. And we look at all kinds of things at the neutral and all this kind of stuff, but we don't spend a lot of time looking at main bonding jumpers and the concept of a main bonding jumper, and we kind of take it for granted. Now, the reason we take main bonding jumpers for granted, and if you don't know what a main bonding jumper is, maybe you're new into the industry, the easiest thing that you probably can relate it to is in your panel, in your house, you have typically, not always, but you might have a green screw in there. And that green screw makes intimate contact between the grounded conductor terminal bus, and the grounding electroconductor, and it all makes connection to the enclosure. So everything gets bonded together. It's happy, and that main bonding jumper is what does it for the most part. Now, there's various variations of that where you could have two separate bus bars and they're connected together with the main bonding jumper, but ultimately it's tying everything together. So the main bonding jumper is the linchpin for making sure that in a fault condition, you've got that equipment ground that's running out there, whether it's green or bare, you've seen it. It runs in that cable assembly, or you pull it in raceways out to receptacles and switches, and it ties everything together. You get that. You understand it. But once there's a fault condition and it gets back to the panel, it's trying to facilitate that current to get back to the source. Now, the source is the transformer, or in a generator, that is your source. Or in a transformer, your source is at the actual secondary of that transformer, where that connection is identical to the main bonding jumper, but it's called a system bonding jumper. And we'll talk about that a little bit in a minute. But let's talk back to this main bonding jumper. So, typically in a residential application, it might be a green screw. And we're talking full finished green screw, okay? Not something that's colored with a Sharpie, okay? It has to be identified with the green finish, and it has to be visible with that screw installed. Okay, so I have to be able to see it. So at the end of the day, that's the easiest main bonding jumper. It comes from the manufacturer. It goes in there. You do nothing, and you just make sure it's installed in the proper location, because there's a right way and a wrong way to install that. And it makes a connection to the enclosure through an opening in the back, which has the two consecutive threads, so it meets all the rules for 250.8 of the NEC, which gives you a list of different types of connection methods for grounding and bonding applications. Now, a main bonding jumper can be a screw, it can be a wire, it can be a bus, it can be something proprietary that is similar from a manufacturer, and it's part of their listing. Now, we're all familiar by now, if you've listened to me for any number of years, manufacturers produce products, they test their products, and if they supply something with their product, then you don't have to rethink it. You don't have to recreate the wheel. If they supply the screw, you use the screw. If they supply no screw, but it is service equipment, and it's suitable for use as service equipment, then it's going to have the ability, whether or not it's a bus bar. And that's another thing. You have a wire. I can take a wire from that terminal, the grounded terminal where everything connects to, over to the enclosure, and that would be my main bonding jumper. Or I could use what's called a bus. So you've seen them, the little bars that are in the panels look like a little Z bar, zinc coated bar, or whatever it would be. That's considered a bus. Okay. And then you might have just a screw like we talked about, or something similar that's a suitable conductor, and that might be supplied by the manufacturer and it might be labeled as such, and that's part of their evaluation. For example, UL 67 panel boards, for example, to make that full connection inside that enclosure, they will usually, with service equipment, they will provide you with the ability to do that. Okay, whether it's a screw or the bus bar or whatever it is, they'll provide it. Now, if they provide it, you don't have to do anything. You don't have to worry about how to calculate it. You just take it for the manufacturer. Yeah, it might look small. Yeah, you might say, God, is that going to handle it? It's been evaluated. It's fine. Don't overthink it. Now, if you choose to not use it and you want to use a wire and size the wire to do it, then you can do that. But you're going to have to do some calculations, and we'll kind of talk a little bit about that today if you choose the wire type. All right? So, again, manufacturers usually will provide this provision for you, but in the fact they do not, you have options. You just have to make sure, one, that equipment is capable of being used as service equipment. Okay, that's the first thing to remember. Also, I'll remind you, if you get a piece of equipment that says rated for service equipment only, then you can't use it as a feeder panel downstream, okay, as a remote distribution panel, because that wouldn't be a service. Now, I can use that equipment in some other aspects of the code, like for generators or something that tells me that it has to be rated for use as service equipment, like SUSE rated. Obviously, that equipment would be, because it says service equipment use only. It's still used as that, and it would be okay. But you can't use it in areas where like a remote distribution panel, for example, because that is not a service. Okay, it's being fed by feeders. Okay, so just kind of read your nomenclature on it, but you know what? Most of these are just say it's suitable for use as service equipment. Doesn't necessarily mean that you can't not use it as a remote distribution panel downstream. You just need to make sure you follow all the rules in 250.24a5 so that you don't have an improper case to neutral. In other words, the neutral is kind of isolated away from the case, whereas the equipment ground does bond to the case downstream. Not what this class is about, but you kind of get the concept. We don't need circulating current because there's always current traveling on the neutral. Last thing we want to do is connect that straight to the case. Now I've got current traveling on the grounds. I got current traveling on the neutral. If I lose a neutral, then I got this current traveling on the equipment ground, which ultimately connects all metal parts together. Not a good thing. Creates a lot of things, objectionable currents. It can create high EMF fields, and people can be hypersensitive to that. All this kind of stuff. And you just can't do it. It becomes an unsafe condition. All right, now, getting back to what we're talking about, main bonding jumper. So the first thing we want to know is, where do we go to give us the general rules for a main bonding jumper? So in the National Electrical Code, we're going to look at 250.28. Now, 250.28 is titled Main Bonding Jumper and System Bonding Jumper. Why? Because they both serve identical functions, just in different sources. Okay, one dealing with the utility, and the other dealing with something like a separately derived system, whether it's a generator, if it's truly separately derived. That's a whole nother episode we probably should do on why there's some are and some aren't. But also transformers, for example. So the sizing of the main bonding jumper or the system bonding jumper is very similar, and they utilize the same table within the National Electrical Code, which is 250.102C1. And we'll talk about that in a minute. All right, so let's kind of go through the list, because there's four things. There's an A, B, C, and D that you got to follow when you're sizing it. So we're going to assume that we're doing the wire type. But we could also do a bus bar type that's not supplied by the manufacturer. And if we do that, then if we're choosing to use the bus bar, then it has to have the same area as what a conductor would be. And there's plenty of calculators out there to determine that and to find out what the area is. And the cross-sectional area of a conductor can be translated to what the cross-sectional area of a bus bar is. So that's not complicated, okay? But just remember, most of the time, people are going to choose a wire to make it simple. All right. Now, if the manufacturer supplies the bus, which again could be just a piece of metal, a lot of people get confused when they say bus bar. They're thinking it has to be a terminal bus bar, but not necessarily the case. All right, a bus is just simply connecting 2 points together, and it replicates. It is a conductor. So at the end of the day, there's certain materials that can be a main bonding jumper or a system bonding jumper. So that takes us to 250.28a, and it says main bonding jumpers and system bonding jumpers shall be of copper or of other corrosion-resistant material. Believe it or not, aluminum is corrosion-resistant. It corrodes, but then it creates this patina because, I'll be honest with you, copper also corrodes. They don't directly say aluminum here, but aluminum is corrosion resistant. Very high level of corrosion resistant. But you have different things with zinc coatings and other things like that that could qualify as corrosion resistant material that you could utilize for this. Okay, let's keep on. We don't want to get bogged down in that. Now it goes, a main bonding jumper and a system bonding jumper shall be a wire, bus, screw, or similar suitable conductor. Okay, well, again, green screw is a conductor, okay, in a sense of what we're doing with it. We're using it as a main bonding jumper, but it's already been done. It's a conductor, not a conductor of the wire type, but it is a conductor of current, okay? So that green screw gets used a lot. The bus that comes with panels gets used a lot, okay? Now, the wire. So if I choose to use a wire, then I'm going to have to do some sizing to that to make sure that that wire is properly sized, okay? Now, I know what somebody's going to say, but Paul, that bus that comes with it and that screw is not very big. And you're telling me that I got to do a wire calculation if it's a wire type, and it might be bigger. It might have a bigger area than what that screw is. And the answer to that is absolutely right. But the wire wasn't tested for use as a main bonding jumper in the same way that that screw was tested, okay, that came from the manufacturer. Okay, so they do their tests. We're making this up in the field. We're choosing to use a wire to make this connection. Okay, and when I say make that connection, guys, again, it's from the actual grounded terminal bus over to the enclosure or over to a separate equipment grounding terminal bus. And we have to tie all this together. And so we have to size. If we choose a wire to do this tying together, then we have to size it. If all of this was on one common bus, just one bus bar in that panel, and I put the green screw through it, that's the one that the white or gray grounded neutral conductor comes to, then I'm pretty much simply done, right? But this is a situation where I might choose to use a wire to make that connection. All right, and if that's the case, then we're going to have to do something extra. Now, let's go on to the next one, construction. It says, where a main bonding jumper or a system bonding jumper is a screw only, okay, like what we see with the green screw in the panels, it says the screw shall be identified with a green finish that shall be visible with the screw installed. That doesn't mean you take a green Sharpie and you mark the head only, okay? This screw, it says the screw, and you can argue to disagree. I don't really care. I'm going to tell you my opinion. Do what you want. But the screw that comes from the manufacturers that is designed for this is going to have a complete green finish if you're using it as a main bonding jumper, okay? It is going to have the complete green finish. Okay, not just one you pull out of a drawer. It's silver, and you start coloring it with a Sharpie. Okay, that one wasn't evaluated for it. Okay, next, C. It says attachment, and again, I should say, you can always agree to disagree with me. I really don't care because I'm the one teaching this. If you're one of those guys that pop in and listen to the podcast and say, oh, it's Paul again with his opinion, kiss off. It is my opinion, and I've been teaching this stuff for 30 years, and I've worked with manufacturers. I've worked with NEMA. I'm intimate with a lot of these manufacturers, okay? You just don't grab a screw and stick it in there because it fits and take a green Sharpie and you make it green. You do what you want to do. That's not what I'm going to do, and I'm going to teach you what I want you to know. Next, C, attachment. Says main bonding jumper and system bonding jumpers shall be connected in a manner specified by the applicable provision of 250.8. So 250.8 talks about screws that have to be listed for grounding and bonding. And so those screws that come with the equipment is evaluated for grounding and bonding. And of course, it's going to have the green finish. Now, also, in the event that I offend anybody by my harshness of that, is that there's a lot of you that listen that really care. And that's why I keep doing these. But there are a select group of individuals, and they're the same ones that just want to be trolls and say negative crap all the time. Usually means they can't teach it, means they don't understand it, or they're embarrassed, or they're intimidated, or they just don't have the same dedication that you have to learn it. And so what? I appreciate you people that say, Paul, you're exactly right. Screw them. keep going. And that's the kind of emails I get, and I appreciate you. So that's what 250.8 is. It talks about the connection, threading, two full contacts, and that's what's already inherent in the equipment if it comes with that green screw, for example. All right. Now, the other way to think about this is the attachment. When that main bonding jumper or system bonding jumper shall be connected in a manner specified in the provisions of 250.8, it could be that I have a panel that has a separate terminal bus for the grounded conductors and a separate terminal bus for equipment grounded conductors, which could be the same bus, but they're separate. So they're connected together with a wire. And that wire would be a main bonding jumper as well, because that again gets us back to the root of what a main bonding jumper's function and what it's designed to do. It's tying this all together. All right. So in that scenario, all of the connections, when it connects to the one bus to the other bus through the proper terminals, pressure terminals or whatever, all of those things have to be met. And we'll assume when you buy the right equipment and all right buses and right lugs and everything, that's being met. When it's not being met is when somebody tries to do something in the field just to make it work. You know, they try to be that MacGyver approach, and they just kind of piece things together. No, you need to use products that are identified for their specific use. In this case, grounding and bonding, because it's vital that you get it done right. Okay. All right. So then we come to D, which is size. How do we size that main bonding jumper? Well, it says in D, it says the main bonding jumper and the system bonding jumper, remember, they're going to be sized the exact same way. The only difference is that in the utility at your service, you're going to size it based on the conductors that are coming from the service. In a transformer, you're going to be sizing it based on the derived conductors from the secondary of the transformer. Okay? No difference for that application. Now, it goes on to say the main bonding jumper and system bonding jumper shall not be smaller than specified in table 250.102C1. So it can't be smaller than the values that are given in that table. All right? Pretty simple in the application. Okay? Now, we've got two little rules here. Actually three, but we'll kind of cover them pretty quickly. Two little additional rules under D for sizing. It says, well, we understand the basic rule in item number 1, D1, which is basically take whatever those conductor sizes are that are supplying it and go to 250.102C1, and we're happy. We go to that table. We go down the table. We see the size, and that tells us what size a main bonding jumper or a system bonding jumper size. It's pretty simple. But what if the provisions of 230.71A, which allows me to have up to 6 disconnects in one location, how do I size the main bonding jumper there? All right, so item number 2, D2 says, well, the main bonding jumper for services with more than one enclosure, it says where the service consists of more than a single enclosure is permitted in 230.71A. Okay, it says the main bonding jumper for each enclosure. So we have 6. Let's say we have 6 service enclosures, and I've got 6 separate ones. They're all services. They're all grouped same location. I have to have a main bonding jumper in every one of those. But when I'm sizing it, I only have to size the main bonding jumper based on the conductors that are feeding that specific enclosure. They're still service conductors, right? But they're feeding that one enclosure, and I size it based on that. So I might have, 5 different enclosures, and I might have 5 different size conductors feeding those 5 enclosures or 6 enclosures, but I'm basing that main bonding jumper specifically on those conductors that are feeding that specific enclosure. Okay, so pretty simple in the concept of how we do the sizing again. All right. Then it goes on to say, number 3 says, okay, what if I have a separately derived system with more than one enclosure? Same concept. Okay. The difference is when I'm sizing for a separately derived system and I have only one enclosure that I'm supplying, then when I'm doing it inside the transformer and I have that system bonding jumper there, I'm basing it on the derived conductors. Okay? And it's pretty simple, just like I would on the conductors that are coming into a utility. I base it on those. Pretty simple. I go to the table, 250.102C1. That table encompasses grounded conductor sizing minimums, supply side bonding jumper sizing, system bonding jumper sizing. That table used to be part of 250.66, which generally was for grounding electroconductors. But there was confusion. Why did we use that table? And it was titled as grounding electroconductors when we needed something specific for grounded conductor minimums, for supply side bonding jumpers, for system bonding. So that's why in 2014, table 250-102C1 was created, and it makes it really a good table for sizing all these things. All right, so we go to that table and we size it. Now, what if we have a same scenario where I have a separately derived system and I've got more than one enclosure? So I've got a transformer that's sized properly, and if you don't know how to do that, go watch my transformer series. There's a bunch of videos that talk you how to do that. But I've got separate panels that are being supplied by one transformer. Perfectly acceptable as long as that transformer is sized properly, right? How do I do this? What do I do about the supply side bonding jumper? Or what do I do about the system bonding jumper? Okay, let's talk about that. All right, so let's start with the very basic one. Let's say that I have a transformer and I have only one enclosure. Now, the code allows me to put this system bonding jumper in the transformer, or I can put it in the first disconnection means. Okay? All right? Either or. Typically not in both. Now, there is an exception to that rule. If it's outdoors and there's no parallel paths and whatnot, then you can have it in both places. But we're not going to teach that today. We're going to say you either pick it at the transformer or you pick it at the first disconnection means. Okay? All right. So, either or. Now, for the single enclosure, this is easy. So, I size it based on the size of the derived conductors from that secondary. And preferably, I've done my calculations. I know what size they need to be. I'm aware of 240.21C1 if it's a 10-foot. I know what I'm doing. I've sized everything the way I want to. Now, the system bonding jumper inside the actual transformer gets sized based on those conductors. It's pretty simple. So, example is, if their derived conductors was a 600 kc mil, then I go to 250-102C1, and I go down, it says 350 through 600 copper, then it would be a 1-aught copper, and that is going to be my system bonding jumper. That's what it would be, and I'm done. Okay. Now, what if the system bonding jumper is in the first disconnection means, and the code allows that application? Now, if that's the case, I'm sizing it as well based on the conductors that are supplying that piece of equipment. Okay. Pretty simple, right? So now that if I have more than one, so what if I have two enclosures? Okay, well, if I have two enclosures and I have this system bonding jumper located at each one of the enclosures, so it's in the enclosure, then I'm still only going to size it based on the size of the conductors that are feeding, and those are called derived secondary conductors, that are feeding that separate panel, and I size it based on that. But what if I want to put this system bonding jumper in the transformer now, and I've got two separate enclosures? Well, let's just do this. What if I have a 500 kc mil derived conductors to the one panel, and I have 600 kc mil set that's derived to the second panel? Since one is 500 and one is 600, and my system bonding jumper is going to be located in the transformer. What does the code say? Well, the code says that it says a single system bonding jumper shall be installed at the source, that's in the transformer, and sized in accordance with 250.28D1, which ultimately sends us to 250.102C1, based on the equivalent size of the largest supply conductors determined by the largest sum of the areas in the corresponding conductors of each system. Remember, I had a set of 500s in the one, and I had a set of 600s in the other? Basically, I just take any one phase, and I take the A's that's the 600 set in the one, and 500 of the A's in the 500 set to the other panel. So that's 6 and 5. Okay, what does that give me? 6, 7, 9, 10, 1100 kc mil. So then, in that case, I then take that as the equivalent sum, okay, as the largest conductor, and then I go to 250-102. And I see what it needs to be. So I go to 250-102 in my code book, and I say, okay, so over 600 through 1100, that's what the combined value is. And if you go look up at the top of this table, you'll see that it says equivalent area for parallel conductors. But the code rules back here in 250.28D3 told me how I do this. Okay, and I have to add up the largest of each set. So that's how we got the 1100. So then I go here and I treat them as one conductor. So it's not over 1100, so it's a 2-aught. So that system bonding jumper that goes inside the transformer is a 2-aught, and that's how you do it. Okay, you see? And so that's how you use it. Now, if it had been a 600 and a 600, okay, and each separate one, then it would have been 600 is 1200. Then when I went to 250-102C1, it's over 1100 kcmil copper. Then I have to follow the notes, and the notes say to treat it at 12.5%, and that's going to be my minimum size. You get me? And that, again, is one of the differences between 250-66 and 250-102C1. People say, isn't it the same table? All they did was copy and paste it. Yeah, the difference is 250.66, the largest grounding electroconductor required is a 3-aught copper, for example. That would be the largest that's required by that table in the copper. But you could also, the largest in aluminum is 250 kcmil. Whereas when you get over to 250-102C1, once you get to 1100 copper or 1750 aluminum, then it kicks in the requirements for you to apply 12.5%. So the conductors can be larger under this, and the reason is lightning is what it is when it comes to the application of 250.66. When it comes to fault current, it really is dependent on the overcurrent device and how much it allow to be on there and what type of fault you're dealing with. So when you're dealing with bonding jumpers and things like that, you have to account for that. So that's why you have to go up to the 12.5% rule once you get over 1100 copper, 1750 aluminum. Okay, so that's kind of how you size the application when you're doing a system bonding jumper. Okay, pretty simple, right? No brainer. No bueno, right? No problem. You all get it. All right, so now let's talk a little bit, kind of to round out this grounding and bonding thing. So that's how you do main bonding jumpers and system bonding jumpers. So now let's move on to, let me talk about generators. So if I have a generator, right, and in that generator, the overcurrent device is in the generator, then sizing the conductor, the breakers in the generator, so sizing the conductor back to the premise or the disconnect that might be at the premise, sizing it back, that would be based on whatever the overcurrent device is in the generator. And so that's going to be just an equipment grounding conductor, 250-122, and you're going to size it based on whatever that device is. Now, what if the overcurrent device is not in the generator? Okay, so that is going to be, from there, that is called a system bonding jumper. Okay, and we're going to have to size that the same accordingly based on the derived conductors that come from the generator. Pretty simple, the same as what we would do for the transformer. Okay, no difference there. Don't get bogged down in that. Okay, the only thing I will tell you is make sure that you understand the difference between when something's a separately derived system and when they're not. And for example, in generators, if the transfer switch is not switching the neutral, then it is not separately derived, and you do not want to have at the generator a system bonding jumper. You do not want to have the grounded connected to the grounding. Okay, you want them to be isolated. Now, some manufacturers call for ground rods at generators, and if it is not separately derived and they call for a ground rod, that's perfectly fine, but you make sure that it only connects to the equipment ground terminal. It does not connect in any way to the grounded neutral conductor in any way, shape, or form. And most electricians, you should verify that, because there has been occasions where manufacturers have supplied generators with a system bonding jumper already installed, yet the transfer switch wasn't set up to be a separately derived system because it was not switching the grounded neutral conductor, and that could be a very deadly situation. So please make sure you test everything. If at the worst, do a continuity check between the grounded conductor and the actual equipment grounding terminal on the generator. And I would say do that immediately before you hook up anything, so you don't get a chance of anything backfeeding anywhere and giving you a reading that might fool you. Once you get that generator, immediately check for continuity between the grounded terminal post and the equipment ground, just to make sure there isn't, and just look in there and make sure there's no system bonding jumper installed. Save you a heartache of pain down the road. Okay, so now let's move on to sizing, let's say, a supply-side bonding jumper. So what is we talking about for a supply-side bonding jumper? Now, let's talk about it in the easiest sense to understand it, and that is in a transformer, because I think it's the easiest way to understand what a supply-side bonding jumper is in that scenario, plus what a supply-side bonding jumper is when we're talking about supply bonding to raceways coming into a service panel, for example, or a open bottom enclosure where the conduits are coming up out of the ground and they're metal, rigid, IMC, and you need to bond them because they contain service conductors, and we have to follow the rules of 250.90, and we have to follow all the bonding principles of 250.92 and bond all these things together. So they're on the supply side, right? They're not on the load side of the device. They're not protected by any overcurrent protection device when it comes to in your panel or switchgear. So we had to bond those too. So supply side bonding jumpers can mean a lot of things. For transformers, it can mean what goes from the transformer up to the first disconnection means. But in service enclosures, it could mean how do I bond those raceways that are coming in to this piece of equipment that contains service conductors. So there's a lot of things that we have to remember when it comes to sizing supply side bonding jumpers. And the good news is you're still going to use table 250-102C. Okay? So that's the great thing about it is once you start learning these principles, it's fairly easy to tie them all together, right? So follow along in the code. We're talking about grounded systems, and most of the systems that we deal with in premise wiring, most commercial applications, they're going to be grounded systems. That's not to say you don't have ungrounded systems. There is some application for ungrounded systems, but the majority of what we're going to deal with is grounded systems. And when dealing with the grounded system, when you're doing the supply side bonding jumper, here's what the code says. It says if the source of the separately derived system and the first disconnection means are located in separate enclosures. Now, we're going to use, for our example, we have a transformer here, and we're meeting this 10-foot rule for the secondary conductors, and we're going into another enclosure. So they are in separate enclosures, okay? So the source, where you have the separately derived and the first disconnection means aren't in the same enclosure, okay? Because if they were in the same enclosure, then you wouldn't need a supply side bonding jumper. So they're in separate enclosures, okay? Now, you might need supply side bonding jumpers for service bonding, okay, but we're talking the transformer in this case because we're talking about separately derived systems, okay, and utility's not a separately derived system. Now, the transformer upstream might be, but in our case, that's the utility source, and we're talking about separately derived systems in what we can control, whether it's a transformer that's on the premise that we install or downstream somewhere in the building that we install. That's the separately derived system, and we're talking transformers. We're going to keep it basic today, all right? Now, it's assuming now that the source of the separately derived system and that first disconnect means are not located in the separate enclosure. And that's going to encompass most of our transformer applications that we deal with. It says, a supply side bonding jumper shall be installed with the circuit conductors from the source, and I would say those are the derived conductors, from the source enclosure to the first disconnection means. So the transformer is located in a transformer enclosure. All right, so from there, those conductors, those secondary, those derived conductors go up to the first disconnection means. That's when this is going to apply. And so if that's the case, it says that a supply side bonding jumper shall not be required to be larger than the derived ungrounded conductors. What that's saying is if it's 600 kc mil that's supplying that 400 amp service, see where that happens? A 600 kc mil is a feeder or secondary conductors supplying the disconnection means for a 400 amp rated device for maybe a panel board application. See how that can happen? All right, so those secondary conductors are supplying it, okay, and they're derived, and they're the derived ungrounded conductors, okay, HOTS if you will. It says that supply side doesn't have to be larger. So when we do the calculations and all, it doesn't have to be larger than 600. It really doesn't. Okay? All right, so it goes on to say first, trust me, it doesn't need to be higher than 600. That's what it says here. You're good to go. But it says that supply side bonding jumper shall be permitted to be of non-flexible metal raceway type or of a wire or bus type as follows. So I could use rigid, intermediate. I could use EMT. All of those are non-flexible metal raceway types to be used as a supply side bonding jumper. Okay? So in that scenario, I might have, if it's three-phase, I might have phase A, phase B, phase C, and a neutral going up to that transformer, and they might be using the EMT as the supply side bonding jumper. Okay? There's no equipment grounded conductor because there's no overcurrent device at the actual source connection at the transformer in this case. All right, so that is called a supply side bonding jumper in this scenario. All right, so it runs up, and typically if it's not if it's a flexible type of metal raceway, which are permitted, I'm going to have to install a supply side bonding jumper of the wire type inside of the raceway. Okay, I mean typically that's what we're going to do. Now, how do you size it? Well, let's look at it this way. It says, based on the following, we have an A and a B. And the first one says, okay, a supply side bonding jumper of the wire type shall comply with 250.102C based on the size of the derived ungrounded conductors. Okay? All right. So in this case, I've got a raceway coming up to it. And for that raceway, I'm installing a supply side bonding jumper in that raceway. Then I have to size it based on those derived conductors. Kind of simply what we were doing before, right? I'm going to go to 250.102C, and let's say those were 600 kcm's running in there, and that's with the ungrounded conductors. I just take one phase A. I don't add them all up. I just take the A, it's in there, and then I come to 250.102C1. I go down. It says over 350 through 600, 1/0 copper. So that's what's going to go in there, a 1/0 copper. Pretty simple, right? All right, so the next one we look at and go, B goes, okay, well, a supply side bonding jumper of the bus type shall have a cross-sectional area not smaller than a supply side bonding jumper of the wire type as determined in 250.102C. So if I have some type of application where I'm going to use a bus as the bonding jumper to make this connection and be considered a supply side bonding jumper, I just have to make sure that what size conductor would I use if it was of the wire type, and I have to determine its cross-sectional area, and then I have to select a bus, okay, that is at least the same cross-sectional area as with the conductor. Now I can do the math to find out what the cross-sectional area is of a conductor based on its size, okay? And so all I got to do is make sure that if the application was for a bus type supply side bonding jumper, and I very rarely see those, but if it was the case, then if that was the case, then I need to make sure that it is not smaller than what it would be as if it was a wire. So I might have a transformer that's feeding a bus duct system or whatever, and that's concept where that supply side bonding jumper is actually a bus, and I just have to make sure that the cross-section area would be equivalent to what it would be of a wire type if that was what the selection was. Okay? Make sense? All right. So that's how you size a supply side bonding jumper in that scenario. Okay? Now I'm going to take this, because I said I would, I'm going to take this to the extreme now where I'm talking about bonding on the supply side for things like service raceways and things like that. So let's kind of move into that for a second in that type of sizing. Okay, the first thing that a student of the code will learn is that we were embedded in the rules of grounding. And immediately when I start talking about the raceways that are coming into an enclosure like an open bottom or some kind of panel or switchgear, we shift and we're going to move into part 5, which is dealing with bonding, okay? Tying all these metal parts together. So then we shift and we're in part 5. And then when we're in part 5, that's we're going to look at something that is in 250.102C in general, and look at what it says supply side bonding jumper. Okay? And what we're going to do is we're going to look at how I bond these raceways that are coming in that actually contain service conductors, okay? Because it's on the supply side. And of course, we do have provisions for equipment bonding jumpers that are on the load side, and that's also covered in 250.102, but that's D, and that's not the subject of this topic or this podcast. We're going to deal with the supply side. So I've got, picture this now, a switchgear, or we're going to picture a panel board, and we've got raceways coming in, and they've got service conductors in them, and I need to bond them, okay? And we're going to use our example here to make it simple, I have an open bottom switchgear, and we have rigid metal conduits coming up into the bottom. They're not physically connected to the actual metal case. It's ultimately bonded to the grounded conductor, which is ultimately has a main bonding jumper, which ultimately is connected to a grounding electrode conductor, all that goody stuff. We have got some raceways that are just sticking in the bottom of this enclosure. And now we have to bond these bad boys. Here's how we do it. Now, let's start with the easiest concept. I've got only one raceway coming in. So it's a single raceway. Now, I need to bond it. How do I bond it? Well, the first thing we need to do is look at the rules in 250.102 and understand what we can use as a bonding conductor, if you will. All right. First things first, 250.102. It's titled Grounded Conductor, Bonding Conductor, and Jumpers. And it's various jumpers. Supply side bonding jumpers. You'll notice that we use this for the system bonding jumper. We come all the way to 250.102C1. So there's a bunch of jumpers we use. Okay. Main bonding jumpers, all that kind of thing. And again, we also use this for the grounded conductor as a baseline. Remember, when you're sizing grounded conductors that are neutrals, you have to calculate the load as well in 220.61, and you can't be smaller than what's in this table, and then you take the largest of the two, but that's in a different podcast. It's a different video on sizing grounded conductors, but I want you to see that this is a neat table because this is very all-inclusive. Okay, but you still got to do the load calcs. You can't get away without doing calcs. Okay, so let's get back to what we're talking about. So the material, what can be a grounded conductor, bonding conductor, and jumper? It says material, 250.102A, it says material, bonding jumpers shall be of copper, aluminum, copper-clad aluminum, or other corrosive-resistant material. So here's a neat thing. Remember when I was talking about earlier when it said main bonding jumper says it has to be copper or other corrosive-resistant material? But it didn't say the same thing as it says 250.102A. We probably should change that because if you read here, it clearly states that copper, aluminum, and copper-clad aluminum are corrosive-resistant material. It's not that they don't corrode. They're just highly corrosive-resistant. Okay, now people say, well, aluminum corrodes, and because of that corrosion, you get the aluminum oxide. And that's at terminals, and you have to prepare it properly, no different than if copper corrodes and you're going to make a terminal, you have to prepare it properly, okay? Copper is uniquely different than aluminum, but at the end of the day, a bad termination is a bad termination. But they're both considered corrosion-resistant material. One will corrode faster than the other, but you have to understand the scope of what we're dealing with. It also goes on to say that the grounded conductor, bonding conductors, and jumpers of this material, it also states that a bonding jumper shall be a wire, bus, screw, or similar suitable conductor. So this is specifically talking about the bonding jumper, not necessarily grounded conductor, but it's talking about bonding jumpers. Can be a wire can serve that role, a bus can serve that role, a screw can serve that role, or similar suitable conductor. And again, a conductor doesn't mean a wire type. It means some conductive device that might be provided by the manufacturer. Okay? Not something that you willy-nilly out, but something that they might provide. Otherwise, you're going to be firmly in the screw, the bus, or the wire. And also, a bus is no different than that Z-bar that comes in a panel. That is a bus. Okay? Now, attachment. How do we make these attachments of all these things? Wire, buses, screws, when we connect all them together? It basically says that we have to meet the provisions of 250.8, and 250.8 gives us all of the different acceptable termination methods that we can utilize. Okay, so that's what it's saying. Got to be one of those, got to be listed for its application, grounding and bonding, and if it comes from a manufacturer, it's been evaluated for all that. Okay, so just look at it, and you'll get a list in 250.8. Hopefully you're familiar with that list. Now, move on to C, which is sizing. Okay, so let's paint the picture. I have a piece of equipment, and it has an open bottom because I want to keep it simple. And the raceway's coming in the bottom, all right? And so when it comes into the bottom, that metal raceway, I'm going to put a connector on the end of it, and now I need to bond it. Because it's required to have a bonding jumper to it, because it's anytime I have a connection to a piece of equipment or where it's an impaired connection, whether it's concentric or eccentric or some kind of impairment, and of course the impairment here is there's no kind of connection to an enclosure, so I'm going to need a bonding jumper. Okay, so here's what it says. The supply side bonding jumper shall not be smaller than specified in table 250.102C1. Okay, So basically, the ungrounded conductor that's in that raceway, let's say we have an A, B, and a C coming in, and it's 500 kc mil. That's what each phase is. So I only have to consider phase A. I don't have to take them all. I just take phase A. And what you're going to get is, you go over to table 250-102C1, and you'll see that the table on the left says size of the largest ungrounded conductor, not conductors. Okay, you don't add A, B, and C up. It's the largest ungrounded conductor, all right? Or equivalent if you're running a parallel. So here's our case. We have a 500 kc mil. We go down the left side, and we see that over 350 through 600, if it's a copper bonding jumper, then what we've got here, a supply side bonding jumper, then we've got copper, and it would be a 1/0. So that would be the 1/0 is what we would run to that bonding bushing with a bonding jumper. And we're done. And it connects over to the enclosure. Okay? Done. Happy. That's a bonding. We bonded it. All right? Now, you got to remember that in that enclosure, you also have the main bonding jumper, and that connects the enclosure, connects everything together, so that enclosure is at the same potential as that grounded terminal bus. Thank you to that main bonding jumper. We're happy. Everything's good. So we just have this jumper on it, and it's 1/0, and we're happy to go. And if I take that over to the case, then I got to make sure that that terminal to the case is done in a way that's compliant with 250.8. Some type of threaded entry or a threaded screw. It involves 2 full threads or whatever. It's got to be done properly. And we know the size. That's simple, right? So I can have one. All right, so now let's kick this up a notch. What if I have 2 raceways coming in the bottom and they're paralleled? Okay, so I've got two raceways with A, B, and C in each raceway, and they're all 500 kc mil. Okay, that's what we've got. So we look at 250-102C, and remember, all we're doing is trying to bond that raceway. Okay, and it says size for parallel conductor installation in 2 or more raceways or cables. It says where the ungrounded conductors are paralleled in 2 or more raceways or cables, because I could use MC cable if I want. If it's coming in underground, it's going to be PVC jacketed MC, of course. It says, and an individual supply side bonding jumper is used for bonding these raceways. The size of the supply side bonding jumper for each raceway and cable shall be selected from table 250-102C1 based on the size of the ungrounded supply conductor in each raceway or cable. So let's stop that for a second. Here's what we're saying. If I want to take one single supply side bonding jumper over to that one raceway, then I base its size just like we did before in C1. I base it on the conductors that are in that specific raceway. So phase A is 500. It's still going to be a 1/0. Okay, supply side bonding jumper. Now, I would do that for that one raceway, and then I would do the second for that one. Now, there's a better chance that if I have a bonding bushing with a lay-in lug, that I'm going to be able to use a 1/0, and I'm going to be fine, and it's going to fit in there nicely, and it's rated, because those lugs are going to have a range of conductors that are acceptable. Now, here's the second option. What if I want to run, instead of a separate one to each one of those raceways, what if I want to just run one and kind of loop it through them? Well, the code allows for that. It goes on to say, a single supply side bonding jumper installed for bonding 2 or more raceways or cables shall be sized in accordance with 250-102C1. And so 250-102C1 is going to tell us that you do it just like it was a single raceway. Okay, like all of those conductors in a single raceway. And that's when it sends you over to table 250-102C1, and that's where you read equivalent area for parallel conductors. So in that table it says, oh, okay, well, I've got 2 conductors in parallel. I still only have to take phase A. So I've got a 500 in one, and I have a 500 in other. I'm going to treat them like a single conductor now, because that's what paralleling is all about in 310.10H. And so that is 500 and 500. That is a total of 1,000 kc mil. So then I go down here to this table and I look for 1,000 kc mil, and it says over 600 through 1,100, it would be a 2/0. So I could take one single conductor and bring it down and loop it through both of those raceways bushing, being careful to make sure that that lug can accept a 2/0. Okay, now if it's within that range, then you're perfectly good to go. There will be some occasions where, example, I might have 4 raceways. And if that was the case, it's slightly different, because let's look at that same scenario. We had 4 raceways and we wanted to one single one looping through them all. If that was the case, we take the A phase only in each one of the raceways. So 500, 500, 500, 500. All of a sudden now we have 2,000 kc mil. Okay, so in that scenario, we go to 250-102C1 if we wanted to run that single conductor. We come down the list and we notice that that's going to be over 1,100 kc mil. Well, what does the note say when it's over 1,100 kc mil? Well, it says, well, if that's the case, you're going to apply 12.5%. So we had 2,000 kc mil, which ultimately, to break it down, you take the 2,000 times 1,000, and that's 2 million circular mils. And then you take that value, and you're going to do that times 12.5%. And that equals 250 kc mil. So that means that my single conductor would have to be a 250 kc mil. Well, there's where you start getting to a problem whether or not the lug is sized for that. Because a lot of those lugs will be in a range from up to 4/0, let's say. But they won't necessarily allow you, to take a 250 kc mil conductor. And that's where you become a problem. So ultimately, you'll have to drop back to the individual supply side bonding jumper method and base it on the size of each conductor. So you see the difference where I would get away with running a 1/0 to each raceway, or I could run a 250 and loop through all of them. It's much more harder to deal with, and why would you do that? Okay? I mean, you can if the lug allows you to do it. So that's how you do it, whether or not you're going to do single, or whether or not you're doing a single conductor or an individual to each individual raceway, or you're looping through all of them. Okay, that's the 2 ways. So that's also how you size a supply side bonding jumper when you're dealing with supply conductors, like for utility application. Okay, makes sense? So I think you see that whether you're doing supply side bonding jumpers for transformers, whether you're doing supply side bonding jumpers for supply side of a service, for example, that you get it. Now, when you're making jumpers on the load side, then you're going to use 250-102D, and that's based on the load side, and that's going to get you involved in sizing things based on the size of the conductors, or the overcurrent device is really what's going to dictate that. And you start paralleling things, and then that changes the size of the overcurrent, and ultimately it's going to send you to 250.122. Okay, we're pretty familiar with those when we're sizing equipment grounded conductors, and in this case, equipment bonding jumpers that are bonding maybe the raceways to the enclosures and things like that. So we'll save that for another topic. Hopefully you got something out of it. If I said something that you don't agree with, that's okay. Free country, free world. I talk really quickly, and I try to cover as much as I can. And I do try to keep my podcasts and videos to an hour. Sometimes I go over that. You can stop and pause and always listen to my podcasts for a little bit of time, and then come back later and listen to the rest of it. That's why they got a pause button, friends. So hopefully I didn't bore you to death, and you now understand a little bit more about sizing supply-side bonding jumpers and main bonding jumpers and system bonding jumpers and the secondary conductors when you're sizing the supply-side bonding jumper going to the secondary of a transformer, going to the main, the disconnect on the secondary side. Hopefully you get all that. If you have any questions, like always, you can reach out to me here at Master the NEC or Electrical Code Academy by sending us an email, info at masterthenec.com. Send me your question, or you can go to our website and there's a contact us button there. Reach out, type your question. I'll do my best to try to answer it for you. Again, I'm not a know-it-all, but I know a little, and I try to help and share it with other people. Like me, hate me, I don't really care. As long as you're learning, that's all I care about. And even people that hate me can learn something, so that's a good thing. So until next time, folks, stay safe. God bless.
Every day, the future's getting closer. Every day, the future's looking bright.